Hello, welcome students. We are going to be working on the geology of the ocean floor. As we'll see, there are three components to this lecture. First one is our evidence for the ocean floor, aka bathymetry, a study of the landscape of the ocean floor. Second line of evidence for this lecture is the geologic structures, the hard rock geology of the ocean floor. And then three, sediment. This is sort of that cover that's laid out. And we'll see how kind of all three of these are related to one another and how they play out. The first portion of this lecture will include bathymetry. Second portion of this will talk about the hard rock, the geologic structures, faulting, and major features of the seafloor. The third part will sort of review what we've done with sedimentary rocks to understand the ocean floor. I want to start by showing you this photograph taken from Scripps Institution of Oceanography, and ask yourself, can you see the ocean floor in this picture? No, not. It may be only just a few feet below, maybe a few tens of feet, but you can't see in this picture. What we're going to first look on is the first major term is bathymetry, the study of For understanding bathymetry, we have three options. So the first way for getting a good view of the seafloor is to be James Cameron and make a boatload of money for movies like Avatar and other quality pieces. If you do that, then you can hire the finest engineers on the planet and pilot a submarine to the deepest portions of the trenches. If you're not James Cameron, you're going to have to use some other techniques. First one of these involved towing a weight on a very long rope. The basic principle is this: you are on a boat with a very long rope and this weight, and you're lowering it down. This was widespread in the late 19th century, early 20th century. And this sounds all pretty simple. You've probably, as a kid, tied a rock to a string and seen how far you can lower the string into a body of water. That's a great thing. But it was not that good for, but it's not that simple. Best way to describe it, you remember that the deepest point of the Earth is so deep that you could take Mount Everest, slice it off at sea level, drop it into the Mariana Trench, and if you took Mount Everest and dropped it in the Mariana Trench, you'd still have about 1.5 miles of water above the summit of Everest. That is a long rope. And that rope is going to be heavy even if it's made out of lightweight carbon fiber. And I guarantee you in the 1900s they did not have carbon fiber. What they did do is produce this beautiful map of the ocean basins. We'll expand this window a little bit so you can see a little bit more of it. And you can see they did a pretty good job. Hopefully you can pick out the Mid-Atlantic Ridge. Hopefully you can pick out a couple of these basins on the other side of it. Maybe if you're really discerning, you can pick out some of these trenches over by the Coral Islands. I mean, the number of measurements they had to do and the amount of labor that went into a single measurement must have been spectacular. However, not only that, they were also lowering the rope down. They were picking up all sorts of other things, buckets. Anything they found was probably the first time anyone had ever seen it on some of these expeditions. So coming around the middle of the 20th century, another technique comes online. This is called radar echo sounding, or not sonar echo sounding, not radar. That's what I did in my former life. Sonar echo sounding would basically send a ping. I'm about to do a ping and clap my hands. Hopefully it works in this room. Did you hear that? This is a small room, but even in this small room, there's a slight delay between when you hear the clap coming from my hands and when you hear it echo off the back wall of this room. We can measure that time delay with very accurate equipment. And figure out how far away the wall of the room is, or if you are basically sending a sort of like ping out of a boat, usually this will be a little higher pitched, you probably won't be able to hear it yourself, but sometimes you can. That ping will bounce off the ocean floor. Now, the one drawback with this one is it's a lot faster than lowering a long freaking rope. But you see these things. These are what we call diffraction hyperbola. The problem with sonar echo sounding is that if you have a seamount underneath here, it sends out a fairly wide pulse. So what we're looking at here is that top or blue line is the ocean surface. The bottom is the black line is the seafloor. There's a nice little seamount there. Now, this is the way it ought to look. However, what's going to happen is, as you send your pulse down there, it's going to bounce off. If you send it down, it assumes that whatever it's bouncing off of is directly under the ship, or at least the first thing it bounces off. So, however, if you're close enough to the seamount, it's going to bounce off this thing before it bounces off the bottom of the seafloor. There's going to be this, and so it's going to map your seafloor is up here. As you get closer and closer, that distance is going to get shorter and shorter. And you're going to see this hyperbola shape for the seafloor as your sonar system images it. In short, it was more precise, but fraught with many inaccuracies. Inaccuracies and still limited by where you can get a boat. Now, we're getting better and better at getting boats and ships to new and interesting places. Not only that, we've discovered that if we don't need to get the whole boat to an interesting place. We just have to have the device emitting the sonar signal get to those interesting places. So, more recent advances include the Gloria side-scanning sonar and other sort of devices that are towed behind your ship, and underneath it, they can get a lot closer to the seafloor and kind of keep themselves at about the same depth and constant speed relative to your ship. And this has led to much more detailed images. This also works by sending out beams in multiple directions and measuring how each of those beams, the return from each of those beams, so that you're not only measuring directly what's underneath your device, but also a little bit off to the side. And there's sort of a little trade-off between resolution and coverage, but point being, it's made this map. My own experience with these is that when I was working as a researcher in about 2013, after reading several papers, I designed a computer model that suggested the best way to explain floods in Antarctica was via rivers opening up and plowing tunnels into the sand and mud at the ice-base interface. At the time, no one had seen evidence of these. Shortly thereafter, however, a colleague of mine from Rice University who had been using this did indeed find channels like this right off Antarctica. Now, this is a map of an area where the bedrock's fairly sediment-free. We can see all these interesting features on the scales of tens of meters. I've seen side-scan sonar devices like look at shipwrecks and image individual jars within the shipwreck. And so precision is truly remarkable, and it's helping us see features on the seafloor in a way we would not have thought possible a few decades ago. Now, the final way is to map seafloor from space is, from space. So you can, with all the other mechanisms, you're still limited by where you can get a ship. To demonstrate this, all you have to do is fire up Google Earth. You see all of these little features. These are places where there have been ship tracks. And there's a lot of places where there have simply just never been ship tracks. And remember that the oceans cover about 2/3 of the Earth's surface, so getting a ship there to survey something in detail is just going to be a non-starter for a number of projects. Especially in places like Antarctica. So to remedy that issue, They developed techniques to look at the seafloor from outer space. The basic principle of this works that you have a satellite in orbit. The satellite sends down a pulse. It could be a laser, could be a radar beam, could be all sorts of things, and that bounces off the sea surface. Beautiful thing about this is this can take thousands, thousands, and thousands and thousands of samples, and do so with relatively little effort. And so you're measuring this two-way travel time, and of course, yes, there's waves, there's tides, but if you study stuff closely, you know how to filter this out and get a tide-free vision of the ocean surface. This is where it gets kind of awesome. The ocean surface is not perfectly spherical or even perfectly elliptical. What we're looking at this GIF is an exaggerated picture of what is known as the geoid, aka the height to which water at sea level rise on the Earth. And what you're seeing is you're noticing there's some places where sea level is actually quite a bit closer to the center of the Earth by up to about almost 100 meters than it would be other places, including part of the Indian Ocean, which is almost 80 meters close to the center of the Earth than would be expected, just assuming rotation, and some places in the tropical West Pacific where the sea surface is substantially higher. What's going on in these pictures? What we're seeing in these pictures is the effect of objects on the seafloor, and sometimes even deeper, on the gravitational field. So the principle is that the rocks on the seafloor are quite a bit denser than water, so there's quite a bit more mass. If you remember the theory of gravity, mass attracts mass. So that what you have right here is, over areas of high mass, the ocean surface will be a little further from the center of the Earth. And these satellites can pick that out. And to give you a sense of just how important this is for bathymetry, this has been a game changer for mapping the seafloor. About 19 out of 20 seamounts were not known even 15 years ago before this technique came online. Other things we'll be able to do is map out more fracture zones, map out a lot more features. Additionally, you can see here on South America, we've been able to actually remove some of the sediment cover and back out which parts of South America used to fit together like puzzle pieces before the whole thing broke apart during the opening of the Atlantic. We've been able to map many fracture zones, many seamounts in excruciating detail. We've been able to pick out spreading ridges in what is now the Gulf of Mexico. It's covered with salt and other debris. And get a much clearer sense of what our past Earth might have looked like. And a lot of the stuff's not in your book yet, but it is coming online. And finally, seismic reflection. Just like you could have a ping go down to the Earth and bounce off the seafloor, you can also send a ping down and have it bounce off things beneath the seafloor. Every layer of sediment, there's going to be a slight change in acoustic properties that's going to create a reflection. Reflection. And so we can image not only the sea floor, but also plenty of objects beneath it, faults, sediment piles. One of my best friends from graduate school made his fortune mapping drilling hazards in the Western Pacific Basin in and around Indonesia. And he's doing better than I am. And a lot of us using this seismic data to pick all those hazards out.